Okay, hello everyone in a new video. So we have reached part 7 of chapter 5, which is the chapter of kinematics for grade 11 students. Then now let me complete the explanation of this chapter, and we have reached section number 3, which is tangential and normal acceleration. And now in order to understand what's happening, let me consider the following sketch in an xy plane. Now suppose these axes are labeled by the positions x and y respectively. So this is x having the unit meter, and this is y having the unit meter. And here let me say that these x and y are different than the ones that we use in mathematics, simply because they carry units. Okay, so this is the position and this is the position. And let me consider that this is the origin O, and this is the unit vector I describing the x-axis, and this is the unit vector J describing the y-axis. Okay, and let me consider the following trajectory. And here, let me be precise, this curve represents the variation y as function of x. So in other words, it's a relation between y and x, and the relation between y and x represents the trajectory. So this curve here represents the actual path of a particle m moving in the plane. So for example, a particle m moving on a table, okay? Now, we can talk about the position vector. Which is r. So the position vector r is the line joining the origin and the center of gravity of the moving particle. Now this is a vector, so this is the vector r. This is a vector having 4 properties: point of application, line of action, direction, magnitude. So in this case, always the point of application is O. The line of action is always the line joining the points O and M. The direction in this case, it's given by upper to the right. And as for the magnitude for this position vector, suppose that we are writing r in the Cartesian coordinates. So xi plus yj then the length of this vector, or the magnitude, is given by r, which is the square root of x squared plus y squared. So let me recall that given any vector v, say for example, or the vector a, which is written as ax I plus ayj, then its magnitude a is given by the square root of ax squared plus ay squared. So whenever we need to determine the magnitude of any vector, we can use this relation. So we are saying that r is equal to the square root of x squared plus y squared, and this is trivial. Why? Because if you consider this dotted line, so this height here represents y, this is y, and this distance here represents x. So this is the hypotenuse of this triangle, so this is 90 degrees, so this is simply given by x squared plus y squared, okay? Now this is the position vector. As for the velocity is given by the vector v, which is equal to vxi plus vyj. And now let me discuss the properties of this vector, and let me start by the point of application. So always the point of application of the velocity is the center of gravity of m. The line of action is tangent to the trajectory, and the direction is tangent to the trajectory, and as for the magnitude of the velocity, which is given by v without a vector, represents the speed, which is also given by v is equal to square root of v of x square plus v of y square. And here let me sketch the velocity vector on this trajectory, okay? So first of all, notice that the point of application of this vector is the center of gravity of m. So the center of gravity of the moving particle, because it's a particle, then the center of gravity coincides with the point itself. So we must draw the velocity somewhere here, like this, okay? Then they are telling me tangent to the trajectory. Notice that this part of this circle, if you consider here the point A, the part of this trajectory, this can be approximated as a circle. So this trajectory from A to B can be considered as an arc of a circle of radius r. Then we will call r to be radius of curvature. So I repeat that along the path from the points A to B, this part can be considered as an arc of a circle of center I and radius r. We call r to be the radius of curvature. This is the curvature here, okay? Now recall that we are interested in representing the velocity vector without using a scale. So here they are telling me tangent to the trajectory. So tangent to the trajectory, as if this is a circle, so it will be perpendicular to the radius. So the velocity vector will be represented like this. Making an angle 90 degrees with a radius, okay? So why we could have drawn this vector, for example, to be to the left, but I'm supposing that the particle is moving from left to right, okay? So this is the velocity vector, v. So this is tangent to the trajectory. Now I'm representing, okay, the length of this vector is v. I'm representing this vector without using a scale. So this is 90 degrees. Now the more important one is the acceleration. Which is given by a is equal to axi plus ayj. And here let me list only two properties. They are given by the point of application which is also center of gravity of m. As for the magnitude, I will not list the line of action and the direction. Now we will see why. Which is given by a is equal to square root of ax squared plus ay squared. Now using these bases, we call these bases to be the Cartesian bases. So these bases are known as to be the Cartesian bases. So it's a bit difficult to represent or to sketch the acceleration vector and the Cartesian bases. So it's more convenient to go to another basis which is called the Frenet bases. Instead of writing the acceleration as a is equal to axi plus ayj, we will go to another basis in which the acceleration will be represented as at ut plus an un. At represents the tangential acceleration, an represents the normal acceleration, ut represents the tangential unit vector, and un represents the normal unit vector. So let me write down here that a is equal to at ut plus an un, and let me introduce each quantity. At represents the tangential acceleration, ut represents the tangential unit vector, whereas an represents the normal acceleration, and un represents the normal normal unit vector. So now this can be also written as a tangential plus a normal, in which a tangential is equal to at ut and a normal is equal to an un. Okay, so the acceleration a can basically be decomposed into two accelerations, at plus an. So whenever we know at and an, we will determine a. So what does at represent? At represents the tangential acceleration. So it's the acceleration tangent to the trajectory. So it is along So this is a tangential, which is tangent to this curvature. Now the normal acceleration, which is along the radius, like this, toward the center of the circle, or the center of the curvature. And because we have said that a is equal to an plus at, then the acceleration a is determined by completing this parallelogram. So this is the acceleration vector a. Okay. So in brief, if you want to determine the acceleration vector, it's more convenient to go to the Freinet basis, in which the acceleration is represented in terms of the tangential and normal acceleration. The tangential and the normal acceleration are more easier to plot or sketch, and whenever we have plotted at and an, we can complete a parallelogram to sketch the acceleration. Okay, but here what's important for us. Okay, so we have four quantities to determine: at, as well as ut, as well as an, and un. But for this chapter, we'll only consider the tangential unit vector and the normal acceleration. Okay, so how do we calculate the normal acceleration? The normal acceleration is given by an is equal to v squared divided by r, in which r is the radius of the curvature, and the SI unit is meter because it represents a distance. V is the speed, okay, expressed in meters per second. An is the normal acceleration, and since it represents an acceleration, then its unit is given by meter per second square, okay? Now as for the tangential unit vector, by definition the tangential unit vector, which is denoted by ut, now u stands for unit, t stands for tangential, it's given by definition the velocity divided by the speed. So v is the velocity, expressed also in meter per second. V is the speed, expressed in meter per second, and ut is the tangential unit vector. And here let me note the following, that the tangential unit vector has no units. All unit vectors have no units, in a sense. The unit of I is equal to 1, no unit, okay? The unit of j is equal to 1, no unit. The unit of ut is equal to 1, no unit, and the unit of un is equal to 1, which means no unit, okay? Now I'll notice that in this equality we have vector on the left and vector on the right, so this is a vectorial relation. Okay, so the first formula that we should memorize is this, and the second one is this, okay? And here let me make the following important note. Reason behind the acceleration. So the reason behind the acceleration is due to the change in velocity. Okay, so whenever the velocity changes, there is acceleration. Now velocity, recall that velocity is a vector and can be characterized by two quantities of our interest, and it's given by the direction and by the speed. The point of application is not important for us. Whenever I say direction, I'm already speaking about the line of action. So now the velocity can change in two ways. Either the direction change or the speed changes. Whenever the speed changes, so let me say a change of speed causes tangential acceleration. A change of direction causes normal acceleration. So always the change in velocity causes acceleration. Okay, let me write them down, this because they are very important. always the change in velocity causes acceleration. But velocity can vary. So here by vary I mean changes. Can vary in two different ways. And this is due to the fact that velocity is a vector quantity. Okay. Velocity can change in direction and in magnitude. And when I say in magnitude, I mean the speed. Variation in direction causes normal acceleration. Variation in magnitude, which represents the speed, causes tangential acceleration. After justifying the reason why there is acceleration, which is due to the change of velocity, which is the change of direction or change of magnitude, for this reason we have, it's more convenient sometimes to decompose the acceleration into the Frenet bases. Okay, so one should always keep in mind that the acceleration may not only be due to the change in speed, but also due to a change in direction. Okay, and here let me remind you of the following formulas before we move to the following exercise. That the average velocity is given by delta r divided by delta t, in which delta r is the displacement given by r2 minus r1, and the average acceleration is given by delta v divided by delta t. Okay, so now let me solve exercise number 18. They are telling me in a plane motion the position vector of a moving particle is given by r is equal to ti plus t squared j. The radius of curvature of the trajectory at t1 is equal to 1 second is r is equal to 5.59 meters. Now in number 1 they are telling me determine the velocity vector at any instant. In order to determine the velocity vector we need to study the type of motion along the x-axis and the y-axis. And here let me list on the scratch. In the case of URM, x is equal to vt plus x0, v is equal to a constant, and the acceleration is equal to 0. As for the case for UVRM, we have that x is equal to half at squared plus v0t plus x0, v is equal to at plus v0, and the acceleration is equal to a constant. So whenever we need to study the motion, we will refer to these equations in order to indicate the linear and the quadratic terms. Now in number 1 they are telling me determine the velocity vector at any instant, in which the velocity vector is given by vxi plus vyg. Okay, so let's start by studying the motion along the x-axis. So okay, and the parametric equations in this case, they are given by x is equal to t and y is equal to t squared. Now since x is equal to t, so notice that the position is linear in time. Whenever the position is linear in time, we are discussing URM, verifies the general form x is equal to vt plus x0. Now here, because we are talking about two dimensions, so it's important that we distinguish between vx and vy. Then the type of motion is URM along the x-axis. And by this now we can use all of these equations that are given by x is equal to vxt plus x0. Vx is equal to a constant, whereas the acceleration ax is equal to 0. Given that x is equal to t, so by comparison, comparing linear terms, we can see that Vx is equal to 1 meter per second. Okay, so we have already determined Vx. We are not interested in determining x0 or talk about to discuss Ax, simply because we are interested in determining the velocity vector. Now we will do the same discussion, but as for the y-axis. So let me write here as a title motion along the y-axis. Now y is equal to t squared. Let me say since y is equal to t squared verifies the general form. So notice that in this case the position is quadratic in time. Quadratic in time means that the motion is UVRM. Verifies the general form, which is given by y is equal to half at squared plus v0t plus y0. Okay, in this case, because the motion occurs in two dimensions, we need to distinguish between different components, then ay, v0y. In this case, then the type of motion is uvrm, and in this case directly we can use the following equations of motions that are given by y is equal to half ayt squared plus v0yt plus y0, and vy is equal to ayt plus v0y, and ay is equal to a constant, in which the given time equation is given by y is equal to t squared. Then let me say by comparison, we are interested in determining Vy. In order to determine Vy, we need to determine Ay and V0y separately. Comparing quadratic terms, we can notice that half Ay is equal to 1, which means that Ay is equal to 2 meters per second squared. As for the linear term in the given form is absent due to because V0y is 0, and in this case V0y is equal to 0. Then replacing this constant in the following equation, we get that Vy is equal to 2t plus 0, then Vy is equal to 2t. Now after we have determined Vx and Vy, we can safely say that the velocity vector V is given by I, 1 multiplied by R, plus 2t multiplied by the unit vector G. Okay? So this is it for part 1. Now in number 2 they are telling me calculate the instantaneous speed at t1. So in order to calculate the instantaneous speed at t1, first we need to determine the expression of the instantaneous speed as function of time, and then we replace the value of t by t1, which is given by 1 second. So what does the speed represent? The speed is the magnitude of the velocity. But we know that the velocity is given by I plus 2tj. Since the speed is the magnitude of this vector, so it's given by v, we drop down the vector, so this is the magnitude, and by definition the magnitude of any vector can be computed by using vx squared plus vy squared Now the value of the x component is given by 1 to the power 2 plus 2t to the power 2. Okay, so this is the instantaneous speed expressed as function of time. Now we are interested in determining v1, which is the speed computed at the instant t1 is equal to 1 second. So replacing t by 1, we get that this is equal to radical 5 meters per second square. Then the speed of the moving particle for the time t1 is equal to 1 second is given by square root of 5 meter per second. So for example, now we know the magnitude of the speed. What are the other properties? We know the magnitude of the velocity vector, which is the speed. What are the other properties? Point of application is the center of gravity of m, of the moving particle. Here it's not named by m. The line of action is tangent to the trajectory. The direction is tangent to the trajectory, and this is the magnitude. Whenever we have a scale, we can represent this vector. Okay. Now in number 3, they are telling me to determine the acceleration vector. Great. Then the acceleration vector is given by a is equal to axi plus ayj. Now referring to the types of motion indicated in part 1, we have that a of x is equal to 0 and a of y is equal to 2. And in this case, the acceleration vector is given by 0i plus 2j. So it's equal to 2j. Now in the same part, they are telling me to deduce its magnitude. This is a vector quantity, the magnitude corresponding for the fourth property of this vector. So we drop down the vector, and it's given by a is equal to square root of ax square plus ay square, which is given by 0 plus 2 to the power 2, which is given by 2 meter per second square. So whenever the vector consists of one component, then its magnitude will be simply the number multiplied by the unit vector. Now in part 4, they are telling me to determine the displacement vector delta r between the instants t1 and t2. So we are interested in determining the displacement vector delta r computed between the two instants t2 and t1. So it's given by r final minus r initial. Let's determine which of these are the initial instant and the final instant. So the final instant is given by t2 is equal to 4 seconds, and the initial instant is given by t1 is equal to 1 second. Why? Because simply 4 seconds is greater than 1 and time always evolves positively. So it's given r computed at the instant t2 minus r computed at the instant 1. R computed at the instant t2 is given by r replacing t2, which is equal to 4 seconds. Now the expression of r is given by ti plus t squared j. Replacing t by 4, we got this. Now as for r1 computed at the instant r, t1 is equal to 1 second. Simply we replace t by 1 to get I plus j. Now the displacement delta r is given by r2 minus r1, which is equal to 4i plus 16j minus I plus j. Now 4i plus 16j minus I minus j, which is equal to 4 minus 1 multiplied by the unit vector I. So taking I as a common factor plus taking j as a common factor, we get that the displacement vector is given by 3i plus 15j. Then in this case, the displacement vector delta r between the instants t2 and t1 is given by 3i plus 15j. Now moreover they are telling me calculate the average velocity v average between the instance t1 and t2. So the same instance. Now the average velocity by definition is given by delta r divided by delta t. So notice that this is a vectorial equation. Vectors must exist on the left and on the right, which is equal to r2 minus r1 divided by t2 minus t1. No need to calculate the quantity r2 minus r1 again because we have already computed it, which is given by 3i plus 15j. As for t2 minus t1, it's given by 4 minus 1, so this is equal to 3i plus 15j divided by 3. So this is two fractions having common denominator 3, then let's split them out. It's given by 3 divided by 3i plus 15 divided by 3j, which is equal to I plus 5j. Then the average velocity in this case is given by I plus 5j. Knowing the average velocity, for example, in this case, one can calculate the average speed, which is given by v average, which is the square root 1 plus 5 square, okay? Now in number 6, they are telling me to determine the average acceleration A average between the instance t1 is equal to 1 second and t2 is equal to 4 seconds. Great. So we are in number 6. The average acceleration is given by delta v over delta t, and here by delta we are varying with the two instances 2 and 1, so it's v2 minus v1 divided by t2 minus t1. We have computed this quantity, but now it's left to compute this quantity in order to determine this quantity. So what does v2 represent? v2 represents the velocity computed at the instant t2 is equal to 4 seconds. So we need to refer to the expression of the velocity as function of time. The expression of the velocity as function of time is given by this. So it's given by I plus 2tj. Now replacing the value of t by 4, we get this expression. As for v1, it's the velocity computed at the instant t1 is equal to 1 second, which is equal to I plus 2tj. Replacing t by 1, we get I plus 2j. Now we are ready to calculate the variation delta v in order to determine this average acceleration. Delta v is equal to v2 minus v1, which is equal to I plus 8j minus I plus 2j, which is equal to I plus 8j minus I minus 2j. Now taking I as a common factor, we have 1 minus 1 multiplied by the unit vector I plus 8 minus 2 multiplied by the unit vector j. In this case 0I. I've done something wrong. Let me check. T. Okay, no, everything is correct. Plus 6j, so it's equal to 6j. And now the average acceleration, which is equal to delta v divided by delta t. So this is equal to 6j, and the value of delta t we have computed previously is equal to 3. So this is a fraction. Simplifying this fraction is given by 2j, and the unit of the average acceleration is given by meter per second square. Okay. And now we come to the more interesting part. In number 7, they are telling me determine the magnitude of the normal acceleration at the instant t1 is equal to 1 second. So in order to determine the normal acceleration, first we need to refer to its definition, which is given by the normal acceleration. So here, without a vector, okay, whenever they tell us normal acceleration without a vector, because we don't know how to calculate the tangential the normal unit vector. Okay, so we will refer to it as the magnitude, which is given by v square over r. We are interested in determining the normal acceleration at which instant. At the instant t1 is equal to 1 second. So moreover here they are telling us the magnitude of the normal acceleration. Okay, so we are computing it at the instant t1 is equal to 1 second. So this is an computed at the instant t1, which correspond to the speed v1 and radius of curvature r1. So notice that the speed is function of time because it's varying, and the radius of curvature also is function of time. Now v1, have we computed? Okay, we have computed in part 2 the speed at v1, the speed at t1, which is given by radical 5, and eventually the radius at this instant is given by 5.59 meters. So radical 5 to the power 2 divided by r1, the value of r1 is given by 5.59. Plugging this on the calculator, then it's given by 0.89 meter per second square. Okay, now in part 8 they are telling me to determine the tangential unit vector of ut at any instant t. So by definition the tangential unit vector is given by ut is equal to the velocity divided by the speed. Now we have already we need to determine ut as function of t. We have determined the velocity v as function of t, and it's given by this. So it is I plus 2t j, whereas the speed as function of time is given by this expression. And now this is the addition of two fractions having this common denominator, so we can split them out. It's given by 1 divided by square root of 1 plus 2t square multiplied by the unit vector I plus 2t divided by square root of 1 plus 2t square multiplied by the unit vector j. Then the tangential unit vector is given by 1 divided by Now in part 9 they are telling me verify that the magnitude of ut is equal to 1. Now I didn't mention this previously. We call this vector to be the tangential unit vector. We call it unit because its magnitude is equal to 1, as we shall see. So the magnitude ut, so this is a vector having 4 properties: point of application, line of action, direction, magnitude. The magnitude, which is denoted by ut, is the square root of the x component, which is this, plus the y component, which is given by this. Now squaring, we get that 1 divided by 1 plus 2t to the power 2 plus 2t to the power 2, because this power 2 is for the numerator and for the denominator. So this is equal to, now here this is, we can do the common denominator, it will be given 1 plus 2t square 1 plus 2t square, and eventually this is equal to 1. So radical 1, which is equal to 1. Notice that unit vectors hold no units, okay? So I didn't place any unit for this. So indeed ut is equal to 1. And now they are telling me in number 10, calculate the instance at which the speed is equal to square root 17 meter per second. The speed as function of time, so we need to solve for v is equal to square root of 17 meter per second. V as function of time, you have determined V as function of time, and it's given by this expression here. So recall that in the question they are asking us, calculate the instance at which the speed is equal to square root of 17. So we need to calculate time. In order to calculate time, we require that time must appear in an equation, and we need to solve this equation. This equation is given by equating the speed to be square root of 17. Now equating the speed by square root of 17, we can notice that now we have an equation that includes time. What's the type of this equation? This is a quadratic equation in t. So let's square both sides. We get that 1 plus 2t square is equal to 17. So in this case 2t square is equal to 16. Then 4t square is equal to 16. So t square is equal to 4. Then in this case t is equal to plus 2 seconds, or t is equal to minus 2 seconds. This is accepted and this is rejected because time as a measure is always positive. Okay, so that's it for me in this video, guys. Okay, before I wanted to say the following. So in order to have some flavor of what's happening here, let me say the following. That here we have determined that the magnitude of the acceleration is equal to 2, and the magnitude of the normal acceleration is given by 0.89 meter per second square. Now if we refer back to the previous figure, so in this case we have calculated the magnitude of the total acceleration, which is given by 2 meter per second square. The normal acceleration is given by 0.89 meters per second square. Okay, so now this acceleration, the magnitude of this acceleration is given by 2 meter per second square. Okay, part of this acceleration is due to change in direction. So this is an is equal to 0.89 . So part of the change of the acceleration is due to direction, which is this. So notice that if you compare number, this is 2 and this is 0.8. The remaining part is due to the tangential acceleration, which is due to the change in speed. Because here in this exercise, the speed also varies with respect to time, not only the direction. Okay. So as always, the acceleration is due to the change in two things. it is due to the change in velocity, but the velocity, remember, it's a vector quantity. It has a direction and it has a magnitude. Whenever the magnitude changes, then there is a tangential acceleration. Whenever the direction changes, there is a normal acceleration. In this particular case, when the radius of curvature is given by 5.59 meters that we have calculated, at this instant t1 is equal to 1 second. The acceleration is given by 2 meters per second. The normal acceleration is given by 0.889, and we can determine the tangential acceleration. Okay, so that's it for me in this video, guys. In the next part, we'll complete solving exercises on this chapter.